Hi, kids. All right, we're going to talk about the Spring Lab. Some of you may have done it in real life. Some of you did a simulation, and that's okay too. The understanding is the important thing. So let's talk about it. So I have a spring. This is the spring, what it looks like if it's unstretched, and then here it got stretched. A couple things that is important. Hopefully you realize this. So this distance from here to here is the displacement of the spring, which is x. Okay, same thing like if I was starting with the spring here and I smushed it, how much it smushed is going to be the displacement, which is x. Okay, okay, so the other way to think about it is, hey, look, I have a rubber band, okay, and I'm going to just mark off, that's the initial length of it. Well, if I stretch it, my displacement would be from this finger to that finger. So from here to my middle finger there. Okay, so again, it's how much it stretches. You were supposed to take some data and then graph the data. And you were supposed to graph it. So you had Fs over here, which was measured in newtons, force from the spring. And then x, which was your displacement, measured in meters. And you should have gotten, okay, a graph that starts at 0. And this is why it's important that you measure displacement and not the length of the spring, because the spring has a length at the start, but that's not what you're worried about. You're worried about the displacement. So, and as you increase the force as you increase the displacement, the force is bigger and bigger. And you should have noticed this. Well, if I pull this rubber band more and more and more and more, it pulls back on me more and more and more. And you guys already tried that. Okay? So you should have had a graph that looks like this. Hey, that graph is a line. I like lines. You should be able to find the slope of the line. And in fact, you were supposed to find the slope. So now the slope would have been some number, but the units for it would have been newtons per meter. And the slope actually has meaning. So let's say you got 20 newtons per meter. Okay, here's what this means. If I was to stretch this rubber band 1 meter, which I can't, okay, this rubber band is probably a lot more than 20 newtons per meter. It's probably in the order of like, I don't know, 200. But so let's say 200. Let's say you got 200 newtons per meter. If I could stretch this rubber band 1 meter, which I can't. But if I could, the force that the rubber band would exert, it would be 200 newtons, because it's 200 newtons per meter. If I only stretch it a half a meter, it would only exert 100 newtons of force. Okay, so hopefully that makes sense to you. But the slope it does have a special name. It's called the spring constant. And I realize I'm using a rubber band, but same difference. Okay, which the spring constant really is just how stiff is the spring. Okay, so it's just the stiffness of the spring. Okay, if you take a look, I got 2 rubber bands here. Okay, this is a big beefy rubber band, and this is a not very beefy rubber band. Well, guess what? If you were to do the lab with these 2 rubber bands, which rubber band, if you graphed force versus displacement for each one, which one would give you a steeper slope? Well, this one would. Why? Because it's a beefier rubber band. Same thing. If you have a, stiffer spring, you're going to get a steeper slope. Okay? All right. And then you're supposed to, anytime you have a line, you should be thinking y equals mx plus b. And you should think, well, wait a second. I didn't graph y. I graphed fs. The spring constant, I should say, it's a lowercase k. Okay, my slope was the spring constant, which is a lowercase k. And then did I graph x? Oh, actually, I did graph x. So that would be x. And my y-intercept was 0. So, hey, look, here is my formula. Force of the spring equals k times x. Now, if you look on the formula sheet, okay, let me show you. It's right here. I'm going to zoom in. Okay. Now, you'll notice the College Board does a couple things. They put a little arrow. What's the little arrow there to represent? That's that it's a vector. and then they put absolute values. Okay, you're going to see this kind of a lot. We actually already saw this when we did force up here. Okay, but the force of friction. But the reason you have the absolute values there is that that's the College Board's way of saying, hey, this is a lovely equation to tell you how big the magnitude of the force on the spring, but it's not very good to tell you the direction. Okay, so that, but there it is. So you have it. But you guys also discovered it in your lab here. Let me zoom out. Okay. Okay. And then, yeah, so you should have gotten that, which, again, this is how the College Board's going to write it, just so you have it. Okay. And then you were also supposed to find the area of that. Okay. Well, look, I have a force and a distance or a displacement graph. What is area is going to be, in this case, the area would end up being 1/2 base times height. 1/2, what is the base? Well, the base is x. What is the height? Well, that would be fs. Okay, 1/2 base times height. Well, look, what is, x times force? Well, oh yeah, that's work. Oh, right. If you do this, you would get meters times newtons, which is joules. Oh, that's work. Oh, well, that means that if you wanted to figure out the work that the spring did or that you did on the spring, you would have to find the area of this, which is doing this. Well, let's rearrange this. I'm going to say 1/2 Fs times x equals the work. 1/2, well, what is Fs? That's really k times x times x. Oh, 1/2 kx squared. Interesting. So the work done by the spring is 1/2 kx squared. But remember, if you do work, well, really, this is the work you did on the spring. If you do work on the spring, you had to add energy to the spring. Why? Because you stretched it. Remember, something that is stretched has energy stored in it, which is the spring potential energy, which tells you that your potential energy equation for a spring is going to be this. Okay, and if you look on your equation sheet, you can see that it's right underneath that one. US equals 1/2 kx squared. So if you wanted to find that, you could find that. Okay, and then the last thing to note, and you'll have to be able to do some proportional reasoning stuff with it, but I just want to show you how we could do some proportional reasoning stuff with it graphically. Okay, and then we'll also do it mathematically. So let's say I'm going to make up some numbers. I'm going to say this is 1, this is 2, whatever my units were. Maybe my units were meters, so I'm stretching it a lot. So I'm going from this point to this point. Okay. You'll notice going from this point to this point. Do you see how the force goes up twice as much? Okay. Well, that makes sense. If you look at my equation, whatever happens to x happens to force. If this is doubled, this is doubled. Okay. But going from here to here, I want to make sure you understand the area is not going to be times 2. Watch. Here's the red triangle is the area of the first one. The area of the other one I'm going to do in purple. So I have 1 red triangle, I have 2 red triangles, I have 3 red triangles, I have 4 red triangles. But do you see how this area is really this 1, 2, 3, 4? That means if you were to go from 1 to 2 meters, that the energy stored is not going to be twice as much, it's going to be 4 times as much. Graphically, that should make sense. Mathematically, you should have something that looks like this. Well, US is proportional to x squared. Well, if this is times 2 squared, that means my US is going to be 4. Okay? Okay, hopefully that's good. Bye, kids.